Welcome back. In some of the last videos that we did, we looked at how you could calculate the net electric field for a series of point charges. Okay, and when you dealt with point charges, you could basically say that a single electric field, you could calculate and say that the electric field is equal to K, which is Coulomb's constant, which is basically 9 times 10 to the 9th Newton meter squared per Coulomb squared, times the charge of interest Q, and you divide by the square of the distance between the point of interest and the charge location. And this was completely valid for single point charges. But we have to modify this equation slightly when we don't have point charges. So what I'm essentially going to do in this video is I'm going to calculate the net electric field at the origin, which by the way recall is 0.00. I'm going to calculate the net electric field at the origin due to this green rod right here. And whenever you're not dealing with point charges with electric field, you have to modify this equation slightly. What you're going to use is this equation. You're going to say that a differential element of the electric field produced by a point on that rod is equal to Coulomb's constant times a differential charge element dq divided by r squared. Okay, so let's actually look at what the differential charge element is. Let me draw it right here. So this we'll call this differential charge element dq. Okay, and notice that there's an infinite number of dq's along this charged rod. Okay, you could even draw another dq over here. Okay, and here's the idea with the dq. Notice that its distance from the origin changes depending on which infinitesimally small charge element I pick. Okay, and this would also be a valid dq. But the point is that they're infinitesimally small, and depending on which point I pick, they're a different distance from the point of interest, 0, 0. Okay, so here's the idea with these integrals. Okay, in pretty much every case except for one, which we'll do in another video, you're going to have to get dq in terms of basically y or theta or something like that. Okay, so what we're going to do is we're going to do a technique called equation of differential elements. Okay, so what I'm going to say is that I'm going to say that, let's say I take the total charge of this rod is to a differential element, right? The total charge is to the differential element as the total length is to a differential length element. And since this is on the x-axis, we're going to call that dx. Okay, and I hope that made sense. This is equation of differential elements. I say that I can take the total charge of this rod, and that is to the differential charge element as the total length of the rod is to a differential length element. So on the left side here, I have my charge elements. On the right side, I have my length elements, and so I equate them. So now what I can do is I can solve for dq. So what I'll do is I'll multiply both sides by dq. Okay, I'm going to multiply both sides by dq, and then I'm going to multiply both sides by dx. Okay, so multiply both sides by dx. On this side, on the left side, the dq's cancel. On the right side, the dx's cancel. And let me do this as well. Let me divide both sides by L. So what I'm going to do is I'm going to divide both sides by L. And on this side, the L cancels. And now what I've done is I've gotten a term for dq. And so my dq here, my dq in this equation is going to be q, the total charge of the rod, which I have not given you yet, divided by the total length of the rod, multiplied by a differential length element dx. If this rod had been on the y-axis, I would have picked dy, but since it's on the x-axis, I picked dx. Okay? Now, I haven't shown you this yet, but this term right here, this q over L, okay? This q over L, at least in the case of a rod that's basically really thin, this is called lambda. And lambda is the linear charge density. This is the linear charge density. Okay. Now, in this case, what I'm going to do in this first example is I'm going to give you a total charge that doesn't depend on the distance from, or the distance on the x-axis from the origin. So what I'm going to say is, for this example, okay, let's say that the total charge let's say the total charge is 30 coulombs, which is actually a lot. Okay, in fact, one lightning bolt is about 15 coulombs, so this is a large amount. I'm just doing this to make the math really easy. Okay, so the total charge, Q, big Q, is 30 coulombs. Well, what's the total length of this rod? Well, the total length is going to be its maximum x value, which is 4. We'll say it's meters. Okay, its minimum x value is 1 meter, so that means the total length is 3 meters. Okay, so if you want to find the charge density for a rod like this, you basically say that the charge density is equal to the total charge divided by the length of the rod, which in this case is 30 coulombs divided by 3 meters. And that, just to make the math easy, that's the reason I did that. We get that the charge density is 10 coulombs per meter. Okay? And so if I want to find dq, dq is going to be lambda dx, but we just found out that that's, I'm going to leave off units here, but it's going to be 10 dx. And that's what my term for dq is in this problem. Okay? Now, one thing I'll say, and we'll do this in the next problem, we'll do a problem that's very similar to this, but you can have a q, that is a function of x, assuming it's on the x-axis. So, I mean, you could have a lambda. Let's say you could have something like this. You could have a lambda, we'll call it lambda alpha to distinguish it from this one. You could have a lambda alpha that was, say, I don't know, it could have been something like x squared. Okay, x squared and then coulombs per meter. So it can be a function of where you are on the x-axis. And what you'll do in that case is you'll say that dq in that case is equal to lambda alpha times dx, and that would be equal to x squared dx, and that's what your dq is, and that's what you plug into the other equation. Okay, so you will do that in the next problem. So you can have a charge or a lambda that's a function of some other variable, like here on the x-axis. In this case, I told you that it was a uniform linear charge distribution. So that means that no matter what point I pick on this rod, it has the same charge as if I pick any other arbitrary point on the rod. So that's why I can say that I can find lambda, the charge density, is just Q over L. If this rod right here had not had a uniform charge distribution, not only would your lambda be a function of where you are on the axis, but your charge would have to be as well. So in most cases when you have a non-uniform charge distribution, they'll give you the function for lambda. But in the event that they gave you the function for Q, meaning the Q as a function of X for a non-uniform charge distribution, you would just take the Q function and divide by L. But since it's uniform, we can just take the magnitude of the charge and divide by the length. In this case, that gives us a dq, which is equal to 10 dx. Okay, so now what we're going to do is we're going to take that and plug it in to this differential electric field element. So what we know is that, and let me switch back to using white, we know that our differential electric field element is equal to K, which is 9 times 10 to the 9th Newton meter squared per Coulomb squared, times dq all over r squared. However, notice that the r in this case just equates to the position on the x-axis. Okay, that's all it is. So we're basically going to replace r squared with x squared, the distance from the origin. Okay, now what we can do is we can plug in our expression for dq. Plug in our expression for dq. So what we get is k times dq, which is 10 dx all over x squared. And now let's do this. Let's separate out the constants from the x terms. Okay, so what we're going to get, k is 9 times 10 to the 9th, and that's in units of Newton meter squared per Coulomb squared. So it's already in units of meters and coulombs, so we're basically good just to leave it like this. So this is k, and then we're going to multiply that times 10, okay? And then we're basically going to have the 1 over x squared dx. Okay? And what we're going to do at this point is we're going to do an integral. Okay, so let's integrate every side. In the case of the electric field, we're going to integrate that from 0 to e. And then all of these guys right here, we're going to integrate over the length. We're going to integrate over the length of the rod. And the rod basically goes from x equals 1 to x equals 4. So those are going to be the limits of integration, 1 to 4, and we'll write that for all of these. So we're going to integrate 1 over x squared dx from 1 to 4. So now the goal is to actually compute the integral. So I'm going to rewrite this. I'm going to say that we have 9 times 10 to the 9th times 10 times the integral of, let's actually pull x squared into the numerator to make it x to the negative second dx, evaluated from 1 to 4, okay? And just to simplify things a little bit more, if we multiply 10 to the 9th times 10, we should get 9 times 10 to the 10th times the integral from 1 to 4 of x to the negative second dx. Okay? Now let's actually evaluate the integral. Okay? So we're going to have 9 times 10 to the 10th. What's the integral of x to the negative second dx? Well, what you do is you raise the power by 1, and then you divide by that number. So this is going to become, it's going to become x to the negative first, right? Because I raised this power by 1. It goes from negative 2 plus 1, and that brings it to negative 1. And then I divide by this power, so divided by negative 1, and that's going to be evaluated from x equals 1 to x equals 4. Okay, so now let's simplify this a little bit. I'm getting that this is equal to negative 9 times 10 to the 10th times, and this is going to be 1 over x, right? 1 over x. And then that's going to be evaluated from x equals 1 to x equals 4. Okay? And then all we do now is we evaluate that at the limits. Okay, so this is going to be equal to negative 9 times 10 to the 10th. Let's pull that out front, and then we're going to evaluate it at the upper limit and subtract it off from the lower limit. So what we're going to have essentially is 1 over 4. 1 over 4, that's basically just 0.25. That's 0.25. And then we subtract off 1, that's minus 1.00. Okay, so this is equal to negative 9 times 10 to the 10th, negative 9 times 10 to the 10th times negative, well, this is going to be equal to negative 3 over 4. The negative signs will end up canceling because when you multiply two negative signs together, you get a positive number. And it looks like what we're going to get is, well, 9 times 3 is 27, and we're dividing that by 4, so what we get is approximately 27 over 4 times 10 to the second, or excuse me, times 10 to the 10th, and this is going to be in units of electric field, and since everything was in newtons, meters, and coulombs, this is going to be newtons per coulomb. And in general, whenever you compute an electric field, those are going to be the units that you want to report it in generally. Okay, so we get an electric field of 27 over 4 times 10 to the 10th newtons per coulomb. And remember that the charge was 30 coulombs. 30 coulombs is a massive charge. Like I said, a bolt of lightning is about 15 coulombs. So I really just did this to make the math. I thought it was going to make it easier, but since we were multiplying by k, it looks like it didn't. But I think you get the idea, okay? If you have a large charge, then your electric field that's generated by it is going to be a lot larger. Okay, so I hope this video gave you a little bit of intuition on electric field calculation for a uniform charge distribution rod. See you in the next video.